Hi everyone, today we're going to look at lab 3 for ENL 270, which is looking at some applications of op-amps as amplifiers. So in this lab, we're going to look at 4 circuits. We're going to look at a summing amplifier, a low-pass filter, a high-pass filter, and a band-pass filter. Again, in this lab, we're using the LMC 6462 dual op-amp package. And remember that this has a plus or minus 5 volt supply limit. So this power supply is currently set up with a dual supply plus or minus 5 volts. If you're not sure what that means or unsure how to set that up, I suggest you pause this video and go back and look at the previous labs and make sure you're comfortable with both what that means and how you would set it up. To start this lab off, there are a couple of questions asking about the characteristics of this op-amp in operation. And they relate to some of the characteristics here, which are the non-ideal real-world characteristics of this op-amp. For this lab, we are going to use the waveform generator on the oscilloscope. And remember, this was covered as part of lab 0 as how to set this up. Currently, I have this set up with that coming out of here, and the wave generator is on. The first circuit we are going to look at is the summing amplifier. So I've gone ahead and constructed this circuit here, which is our summing amplifier circuit. Note that there are a couple of questions here about asking you to figure out before you go and test this circuit, what should the inputs and outputs be? And this is something you should always do, is think about what values you expect versus what you measure. And that way you can test your hypothesis and make sure you have something that's actually accurate and what you expect. If it's unexpected, that means it is likely either an error in your circuit or something that you've misunderstood or miscalculated. Okay, so the first measurement we're going to take is to measure the output of just op-amp O. So I've left out this 10 kilo ohm resistor, so to isolate that, so we've only got this half of the circuit here. And we're going to measure the output of this op-amp using a multimeter. So I've hooked the multimeter up to the circuit already. I'll set it to measure a voltage, because we're measuring the output voltage of that op-amp. I'll then turn the power supply on. We read negative 2.49 volts at the output of op-amp O. Okay. Next, we're going to look at the summing amplifier S. So what I'm going to do is turn off the power supply for a moment, and I'm going to connect that final 10 kilo ohm resistor, connecting op-amp O to op-amp S. We're then going to have a think about what the output of op-amp S should be based on its gain. And we can then measure what is actually happening there. Note that we are inputting a 5 volt peak to peak 100 hertz 0 volt offset sine wave out of the wave generator on the oscilloscope and into the circuit. So I'll go ahead and make that connection now. Note that I am removing the multimeter from the circuit as it's no longer required, and they'll help keep the circuit nice and clean. You should look to keep the circuits as tidy as you can. These kind of circuits, especially in this lab, can become very, very messy very quickly, and that can make it extremely hard to figure out what is going on, extremely hard to build, test, expand upon, debug, etc. So make sure you take care with doing that. In this circuit, I am using arbitrarily op-amp B in the package as op-amp O as the first stage. I'm using op-amp A as a second stage. You could have this around the other way as well. Either order works just fine. So to this final 10 kilo ohm resistor in, I'm connecting that from the output of op-amp O to the input of op-amp S. The output of op-amp O I'm using is pin 7, and that is going to connect to the input of op-amp S. Note this is the inverting input. We're going to pin 2. So I'll make that connection now. One thing that is worth noting is that it's often valuable to, on your diagram or schematic, write on which pin numbers correspond to what. It can make debugging a circuit a lot faster, and it can even make construction a lot quicker as well. So I have that resistor hooked up now. I'm going to supply the input of the wave generator on the oscilloscope into the circuit. Remember, we use a BNC, the crocodile clip cable from that, to supply that. The red wire is our positive terminal, black is our negative. Our red is going through a 10 kilo ohm resistor to the inverting input of op-amp S, and the black is then going to our ground reference. Finally, we want to be able to measure the output of op-amp S. So we're going to use an oscilloscope probe and connect that to the circuit to do so. The output of op-amp S comes out of pin 1. So again, I connect the probe of the oscilloscope to pin 1 and the ground terminal to ground. And note again that I am using jumper wires on the end of these, so I don't have to hook on to components or wires in the circuit, which is both messy and can pull things out of the circuit. So I'm going to make that connection now. Once I'm happy with the circuit and I think it's correct, I then turn on the power supply and see what happens. So if I turn them on, you can see something is happening on the oscilloscope. I'm going to rescale that. And we see that there is a sine wave at the output. Blow that up a little bit, it's a bit clearer. So we can see that our sine wave has been shifted up by some amount. If we take some measurements of that, again, we can use the measurement function on the oscilloscope to do that. I clear off whatever is there. We can measure both the maximum and minimum of the signal if we want to. So the maximum voltage is 5 volts. The minimum voltage is about 0 volts. We can also measure the average of the signal to find out what the center of it is. Now, I'm going to measure that across the full screen. And that gets us an average of about 2.5 volts, in this case, 2.47 volts. So we can see that we now have our 5 volt peak to peak sine wave that has been shifted up by 2.5 volts. That is going from 0 to 2.5, 0 to 5 rather than positive 2.5 to negative 2.5. Hopefully that aligns with what you expected from your theoretical calculation. If it does not, stop and pause to think why that is. Make sure you understand what this circuit is doing and how it achieves this output. The last question is asks what happens if we were to increase the amplitude of our input voltage signal. So we currently, remember, have a 5 volt peak to peak 100 hertz 0 volt offset sine wave. Pause the video for a moment, have a think about what would happen if you increase the amplitude of the signal. Then once you've had a think about that and have some idea written down, unpause the video and I will demonstrate what happens on the oscilloscope. So if I go to the wave generator, currently we're at 5 volts peak to peak amplitude. If I increase that, or if I add an offset to effectively increase it, we can see that the top of the signal starts to saturate. So the bottom is still the same. The top of it, however, is getting squished. Remember that we have plus or minus 5 volt supply to this op amp, so it cannot output any more than plus or minus 5 volts. So if you set it up so that in theory, it would output more than 5 volts, it cannot physically do that, and so it will saturate at 5 volts, as it's doing here. If we were to then increase the range even larger, we would eventually get to the point where the negative end would also saturate at negative 5 volts. And you end up approaching a square wave if you do that, which is effectively what a comparator does. So that is our summing amplifier circuit. Okay, so the next circuit we are looking at is the low pass filter circuit, which we've constructed here. So remember from lectures that a low pass filter is used to cut off input signals at above a certain frequency. Hence we call it low pass. It allows low frequencies to pass through unaffected. The cutoff frequency for a first order active low pass filter, which is what we are building here, is given in the lab specification to you. Note that this is in radians per second. If you want to convert that to hertz, you need that factor of 2 pi as well. So don't forget to use that. For this experiment, what we are going to do is use this low pass filter circuit, this simple active low pass filter, and we're going to explore what happens as we vary the frequency of the input signal and use different capacitors. For this lab, we're using a range of capacitors. We have a larger 1 microfarad electrolytic capacitor, which comes as a sort of can style package. And we have a number of film capacitors Here, for example, I've got a 103 and a 104. Note that there is a guide on how to read these capacitor values in this red folder at each desk. There is a guide on this page, capacitors, as to what this numerical code, this 103, 104, and the like means. So make sure you have some idea of what that's about and what is going on there, so that when you're looking at capacitors, you have some idea of how to determine their values. Currently, this circuit has the 102 film capacitor in it, which is, if you convert that using the code, is 1 nanofarad. So what we have done is set up an input sine wave at 100 hertz and half a volt peak to peak with 0 offset. And that is displayed on channel 1 in yellow here. Channel 2 in the green is measuring the output of the filter. You can see at the moment for about 500 millivolts input, we're getting 5 volts output at 100 hertz. You should note that at the moment, this circuit is set up with a frequency well below the cutoff frequency of this filter. So effectively, this capacitor is doing little to no filtering. So we effectively just have an inverting amplifier. And with a feedback resistor of 100 kilo ohms and an input resistor of 10 kilo ohms, we should have a gain of -10. So we have 500 millivolts in, we expect to get 5 volts out, and they should be out of phase with each other because of that inversion, which is what we see here, which the peaks and troughs are perfectly out of phase. To measure the cutoff frequency for each capacitor, what we do is we start at a frequency well below the cutoff frequency that we calculate. We should calculate that for all of our capacitors before we go and measure them. Once we've done that, what we know is that at the cutoff frequency, the output voltage will have reduced by a factor of 1/√2 from what it is at the moment when we're well below the cutoff frequency in what we call the pass band, where there is little to no filtering. So we know that we have 5 volts output at the moment. This is in our pass band, so well away from the cutoff frequency. 1/√2 of that is about 3.54 volts. So what we are going to do is increase the input frequency up until the output voltage drops to 3.54 volts. We then record what that input frequency is, and that is the cutoff frequency of this filter. We then repeat that for the other capacitors. So we have a 1 nanofarad capacitor, a 10 nanofarad capacitor, and a 100 nanofarad capacitor. We also have a 1 microfarad capacitor, but we are not going to use that for this experiment because it's a bit fiddly to set it up because the cutoff frequency is so low. So pause the video and take a moment to calculate what those cutoff frequencies should be for those 3 capacitors. Again, they are a 1 nanofarad capacitor, a 10 nanofarad capacitor, and a 100 nanofarad capacitor. Okay, now that you have those calculated values, we will go ahead and measure what these cutoff frequencies are. So as I said before, the 1 nanofarad capacitor is currently in the circuit. I go to where I have the input signal set up, which is on the wave gen on the oscilloscope, and I select the frequency and I start dialing that up. We can see that the frequency changes with these compressing together as we expect. As we do so, our measurement is going to get a little less accurate. We could use autoscale to rescale the oscilloscope as we go. That's a little bit tedious and unnecessary, though. We can use this horizontal dial here to control the horizontal scale of the oscilloscope manually. So by dialing it up, we can again bring this back into scale. So we adjust these scales as we go. Again, we'll keep increasing the frequency. We're now at about 400 hertz. And we can see the output voltage has dropped a bit to 4.74 volts. So it's decreased a little bit. So we keep going up and up and up. As we do so, we're now at a kilohertz. Our output voltage is now 4 volts. Again, I'm going to readjust the oscilloscope and keep increasing this. We're now at 1.2 kilohertz, and our peak-to-peak output voltage has dropped to 3.7 volts. So we're nearly there. If I dial this up to 1.3 kilohertz, we drop down to 3.62, keep going. At 1.4 kilohertz, we're at 3.46 volts out. So a little bit above where we want to be. I'm going to just tweak this using the fine frequency selection so I can dial it a little more accurately and turn that frequency down a bit until we get closer to 3.54. And we are getting 3.54 about now quite steadily. So we're getting 3.54 volts output at 1.366 kilohertz. So 1,366 hertz. So that is our measurement for the cutoff frequency of this particular filter. Okay, I'm now going to dial the frequency back down to 100 hertz and repeat this with the next capacitor. So that was with the 1 nanofarad capacitor. We're now going to use the 10 nanofarad capacitor, which has the numeric code 103. So I remove the current 1 nanofarad capacitor and replace it with the 10 nanofarad capacitor. We can see that already the output voltage has dropped to 4.22 volts at 100 hertz. So we can see there's already some filtering happening. And again, we increase the frequency until we reach that cutoff voltage of 3.54 volts. And we've hit it at 160 hertz, we've got 3.54 volts output. Finally, we do that again with the 104 or 100 nanofarad capacitor. So I put that into the circuit. And we can see that 100 hertz, we're well below our cutoff frequency, well above it rather. Our output voltage is only 960 millivolts. So we're way, way above our cutoff frequency. So now we're going to dial the frequency down until our output frequency rises, output voltage rises to 3.54 volts. To do so, I'm going to readjust the scale so it stays on the screen nicely. And we can see at 16 hertz, we've hit 3.54 volts peak to peak on the output. So that again is our cutoff frequency for this filter. Okay, so that is doing the frequency sweep for each of those capacitors. The last question for a couple of questions for the high pass filter ask you, first of all, whether those measured cutoff frequencies correspond to the calculated frequencies. If they don't correspond, why might they not correspond? And what is the approximate high frequency cutoff frequency for this circuit according to the op-amp's properties? And the hint there is you need to consider the gain bandwidth product of this op-amp. So this is getting at the fact that the op-amp has an inherent high frequency cutoff, and you need to calculate what that frequency is for this particular amplifier circuit. We're now going to look at the next circuit, which is the high pass active filter. Configuration-wise, this is very similar to the low pass filter. We simply change where that capacitor is. So instead of being in feedback across the 100 kilo ohm resistor, it is now in series with the input 10K resistor. Note for this filter as well, we will also be using the 1 microfarad electrolytic capacitor, which I currently have in the circuit. Note that in general, electrolytic capacitors are polarized, so they only go around one way. If you put them backwards, they can damage and be damaged or destroyed. In this circuit, because we have an AC signal going in, either way around is fine. There is no preferred direction because it's varying back and forth. Provided we're not doing that at too high amplitude or too low frequency, the capacitor will be fine. Okay, the first part of this circuit is asking you to derive an expression for the cutoff frequency of this circuit. I suggest you take a good amount of time working on this and that you ask for help if you need it. This is not necessarily trivial if you haven't done it before. Use the lecture notes to guide you to reach the, to be able to do this derivation. Again, if you get stuck, please ask for help. The next thing we are going to do is the same thing that we did with the low pass filter. We are going to find the measurement of the cutoff frequencies of each capacitor in this filter circuit. The idea is exactly the same. We're going to sweep the input frequency until we reach our output voltage being reduced by 1/√2 of its passband value. Again, at 3.54 volts for this particular circuit. Note that for the high pass filter, we're allowing high frequencies through and cutting off low frequencies. So instead of sweeping from low frequencies to high frequencies, like we did for the low pass filter, we need to go the other way around and sweep from high to low. Okay, so I currently have the 1 microfarad capacitor in there, and at 100 hertz input frequency, our output peak to peak voltage is about 5 volts. So again, we go and we change the input frequency. This time we're sweeping down. And as we do so, our output peak to peak voltage will reduce. And I will rescale the time scale as needed. Again, we'll look for that 3.54 volts. We're currently at 13 hertz and 3.46. So we'll dial the frequency up a little bit. And we hit 3.58 volts at 14 hertz. So about as close as we're going to get without going too fiddly and getting a bit too in detail. If you wanted to, you could use the fine frequency control to find out exactly what it is. For this circuit, I'm not going to bother. Okay, so that means our cutoff frequency with the 1 microfarad capacitor is about 14 hertz. Now we can then change it up to the next capacitor. I'm going to use the 104. To remind it is the 100 nanofarad capacitor. So I remove the 1 microfarad capacitor and replace it with the 100 nanofarad capacitor. Now we can see at the moment we are well below the cutoff frequency. Our output voltage is about the same peak to peak amplitude as our input. So I'm going to increase the frequency substantially until we get back to that 3.54 volts output. You'll notice close to the cutoff frequency, there's a rapid change in that output peak to peak voltage. So this one, I've decided to do this one a little more accurately and sweep that frequency more finely. And we get a cutoff frequency of 167 hertz. Okay, next we use the next capacitor, which is our 103, our 10 nanofarad capacitor, and we do this again. Again, we need to now sweep the frequency up because we're well below that cutoff frequency. An important thing to note about rescaling the oscilloscope as we go is that it's not just that it looks good, it's actually to make the measurements more accurate as well. The accuracy of the oscilloscope literally depends upon how clear what you can see on the screen is. So if it's unclear for you to see, the oscilloscope can't measure it very accurately. So this does really matter. Okay, so now we have our cutoff frequency at 1.42 kilohertz. So that's with the 10 nanofarad capacitor. Finally, we can put the 1 nanofarad capacitor in the circuit and try out that one as well. If I start dialing this up again, So we're getting our 3.54 volts output at a cutoff frequency of 5.93 kilohertz. A couple of things to note is, again, with this one, we want to consider whether the calculated and measured cutoff frequencies correspond. In particular, for this last one, we were looking at this 1 nanofarad capacitor. Take note of the shape of the output waveform. It's quite triangular. Have a think about why that might be. So that is our high-pass filter. Okay, the last circuit we are looking at in this lab is the band-pass filter. So if a low-pass filter cuts off high frequencies and a high-pass frequency cuts off low frequencies, what we can do is stick these together to create what we call a band-pass filter, which allows a band of frequencies to pass through and cuts off everything above and below those bands. This lab has asked us to design one using our results from the previous two filters, our low-pass and high-pass filter. And what we want to do is to set our two cutoff frequencies for each filter. We want the low-pass cutoff frequency to be larger than the high-pass cutoff frequency. Be careful, it's easy to get these two around the wrong way. It often helps to sketch out a little bow plot of what the frequency versus gain should look like, and consider what a low-pass filter looks like and what a high-pass filter looks like on a bow plot by themselves. For this band-pass filter, we've been asked to make the cutoff frequencies about 4 times apart by choosing those capacitors, but choose frequencies within the limits of the Opamps gain bandwidth product. For this circuit, the values I have chosen are a value of 100 nanofarads for the high-pass filter and 1 nanofarad for the low-pass filter. This should give us, according to what we calculated and measured before, about 160 hertz for the high-pass cutoff and about 1.6 kilohertz for the low-pass cutoff. So now that the circuit is built, what we're going to do is actually measure these high and low cutoff frequencies, and we're going to measure the gain of the circuit at what's called the mid-band. So for the band-pass filter, somewhere in the middle of the high and low pass frequencies is our mid-band, is our pass band for this one. Our mid-band frequency, note, is the geometric mean of our two cutoff frequencies. So it's not the arithmetic mean, it's the geometric mean. Okay, so by calculating using those approximate cutoff frequencies, we can find that we have a mid-band gain somewhere around 517 hertz. So if I dial down our input frequency to about 520 hertz, we see we're getting about 4.5 volts at the output. And so that is our output voltage at our mid-band. From that, we can calculate what our mid-band gain is. Okay, the next thing we can do is, again, measure our two actual cutoff frequencies, our low pass and high pass cutoff frequencies. So firstly, I'm going to dial down towards 160 hertz, which is our estimated high pass cutoff frequency. Again, we're looking for that reduction in the output peak-to-peak voltage, in this case for this circuit of 3.54 volts. Again, remember that is a 1 on root 2 reduction. So dialing that down, we get 3.54 volts at 170 hertz. That decreases at 160, it's a little bit lower. So somewhere between 160 and 170 hertz is our cutoff frequency for the high pass filter. And it's about 170 hertz bang on. We can then dial up to measure our low pass cutoff frequency, which we estimate is around 1.6 kilohertz. So I'm going to go a fair way up. Be a little more precise. We find our low pass cutoff frequency is about 1.368 kilohertz. So that is our low pass cutoff frequency. So we've measured the output peak-to-peak voltage at our mid-band frequency, which allows us to calculate the gain at the mid-band frequency, and we've measured our two cutoff frequencies. From that, you can now draw on the back of this lab a bode plot. approximating the behavior of this filter. Note for this, a straight line approximation is perfectly acceptable. So you should end up with, if you're doing an approximation, with 3 straight lines, one for the midband, one for the high pass cutoff, and one for the low pass cutoff. Again, refer to your lecture notes if you're unsure how to do that, or a guide of how to draw bird plots. Note that this is on a logarithmic axis on the x-axis. So take note of that scaling shown top and bottom of the axes. The very last question in this lab is asking about the gain at the midband frequency. The question is that your midband gain magnitude might be less than 10 times or 20 decibels, and why that might be. So in this case, we had a gain that was less than 10 for this particular circuit setup here. And you need to consider why that might be the case. Why don't we get what we would predict as the gain in the midband, which should be our unfiltered maximum gain. In this case, for this circuit, a gain of 10. Okay, that is all for this lab. Hopefully this has taught you something about how we can use op-amps in practical applications as amplifiers and as filters as well. Thank you very much.